Okay, thank you for attending this new video. On this exercise number 2 of the Fourier Transform lesson handout, we will calculate the Fourier Transform of a delta train. This is a very, very important Fourier Transform because it has a wide applications. So first of all, let's remember what's a delta train. A delta train is the following. It's a function of time where we have deltas all over the place in a periodical fashion. Okay, so here to the right and also to the left we have deltas all over the place, and they are separated time, which is in this case t sub s, and the amplitude of all the area of each delta is 1. Okay, all the deltas are the same. Mathematically, we write this as the following: is the summatory in an index k of deltas on t and separated intervals of t sub s, as you can see. This is the mathematical expression of the delta train. Okay, so let's calculate the Fourier transform of this signal. So this is a periodical signal, which implies that what we do is we calculate the first, the Fourier transform, which is our final objective, with an intermediate step, which is calculating the Fourier series first. And once we got the Fourier series, we then straightforward to calculate the Fourier transform. So let's calculate in the first step the Fourier series of the delta train. Okay, so well, the Fourier series of the delta train is, if we have the delta train, as we have seen, it can be analytically written as this, is to express this as another summatory in we can call also the index k or y or whatever you want, or I, or whatever you want, of a series of coefficients that we call a sub k times the exponential ajk 2p 2 pi divided by ts, because here we put the ts, which is the period of the signal, times t, and this is the Fourier series. And all what we have to do is to calculate the coefficients a sub k. Okay, so to calculate the coefficients a sub k, there is the coefficient formula, which is 1 divided by the period of the signal, which in this case is t sub s, and then is integral to any period of the signal. In this case, we can pick, as always, any period, but we will pick this period over here. Okay, the period which goes between ts divided by 2 and minus ts divided by 2. This is the period that we are going to take. So in this case, the limits of the integral will go between minus ts divided by 2 and ts divided by 2. And what we have to put here is the signal x of t times the exponential, in this case is minus jk 2p divided by tst, and we integrate in t. Okay, so now in this case we just put what is xt in this interval. Xt in this interval is delta t, so this will be 1 divided by ts integral minus ts divided by 2 plus ts divided by 2 of delta t times e2 minus jk 2 pi divided by tst differential of t. Well, this integral is straightforward if we remember the sampling property of the delta. Remember that there was a very important property of the delta, which is if we have a function ft and we multiply a function ft times delta displaced to a certain point t0, the result of this is the sample of the function f in the point where the delta is, which is in t0, times delta of t minus t0. Okay, this is the sampling property. In this case, as you can see, what we have is something like ft is this here. Okay, this could be the function ft. Delta t minus t0 is, in our case, is delta t, so in this case t0 is 0. Okay, so in our case all this term will simplify into f in t0, so this exponential in t0, it will be e to 0 times delta of t minus t0, which is 0. Okay, so applying this property here, what we get is 1 divided by ts, integral between minus ts divided by 2 and ts divided by 2, and e to 0 is 1, so in this case we will get delta t dt, okay, which is 1, okay, by also the property of the integration of the delta. So what we have concluded is that all the coefficients a sub k are the same and is 1 divided by ts. Okay. Of course, you can then calculate if you want, or you can write the Fourier series, just put in this expression where ik just substitute it with 1 divided by ts. But let's move forward and let's go to our objective, which was trying to calculate the Fourier transform. And then remember, as we saw in class, that the Fourier transform of a Fourier series, so of an expression like a k times a to j k 2 pi divided by tst, so in other words, the Fourier transform of a Fourier series is 2 pi times the coefficients ak multiplied by deltas, which are displaced a quantity which is 2 pi divided by ts. We saw this as a very important Fourier transform, and this is exactly what we are going to apply here. Okay, so what we want to apply here is a Fourier transform of a train of deltas, okay, of this summatorium k of delta t minus k ts, okay, for which we have calculated the Fourier coefficients, which is this one. Okay, so in this case, applying this formula over here, it will be 2 pi summatory in k of ak, which is always the same, is the same coefficient, 1 divided by ts, delta of omega minus k 2 pi divided by ts. Okay, so this is the result. This is the Fourier transform of a train of deltas. But let's sketch it to get familiar with it. The Fourier transform, then, as it says in this expression, it will be a function, in this case, in omega. And you can see it's also a train of deltas. It's also a train of deltas, as I am putting over here, that goes all over to the right and to the left, to minus infinite. Okay, but with two differences with respect to the original train of deltas. First, the amplitude or the area of the deltas is no longer 1, but 2 pi divided by ts. This is the first difference. And second, the separation between them is no longer ts, but 2 pi divided by ts. So in this case, this delta will be in 2 pi divided by ts. In the second one, it will be in 4 pi. For k1, it's this. For k2, it will be 4 pi divided by ts, and the same on the negative one. Okay, this is the transformation of the original train of deltas in the frequency, and it's something that I encourage you to learn by heart, which is the transformation of a train of deltas of amplitude 1 and separation or period Ts is another train of deltas in frequency of amplitude 2 pi divided by Ts, and the separation 2 pi divided by Ts. Well, I hope it's clear. If you have any doubt, just write me or email me, and thank you for watching. Bye-bye.